Welcome to the Building Performance Podcast, where we talk about trends in high performance building and retrofits. I'm Corbett Lunsford. Today, we are going to go very deep on myth busting, some HVAC stuff, because I'm getting a little bit PO'd out there. There's a lot of misinformation going around. There's a lot of marketing. If you are like me and you're getting confused about which devices might actually help your clients in regular homes and which ones might potentially be setting them up for a homechem disaster, here is the time to talk about that. I am sure that we are about to get our minds blown on a number of levels by Dr. Jeffrey Siegel, who's very generously offered to share his expertise on indoor air quality and HVAC systems specifically. He is a professor of civil engineering at the University of Toronto. Jeff, thank you very much for being here today.
Sure, glad to be here.
Okay, so Jeff, basically, HVAC maniac. He's doing research on indoor air quality, specifically around, in this conversation, HVAC systems. And we're going to talk about international stuff, which the way that they do HVAC in other parts of the world is nothing like this, apparently. And I'd like to just start the conversation with the homechem experiment, which I hope that our audience is familiar with. We have over 40 videos about that. And Jeff was responsible for helping to design the house that was the setting of the homechem project. Can you kind of explain how the systems in that home are configured and why you decided to do it that way?
Sure. So the big difference between the homechem house and almost every other house is that it's got two completely independent heating and cooling systems that are designed to operate together or separately or as they need to be. And that's really strange right from the start, because why we have two systems. But the idea is, look, it's a research house. We want to be able to do things a lot more than we would in a normal house. There are times when there are research objectives which are different than normal house. That's not it, though. There are some other things that make it different, too. And one of the big ones is you might have noticed when you're in the house that there's a lot of airflow. Right. And so a typical house gets something like, when the fan is operating, it runs, let's say 4 house volumes per hour go through the HVAC system. In either of the two systems in the homechem house, 8 air changes an hour go through it when it's operating. So it's really moving, I would say, much more air than
in either. And both of them often might be running.
Yeah, I mean, it depends a lot on the experiments going on, but there is certainly that capacity, right? And so that's a lot of flow. And that really changes things. Now, that's desirable if you're doing experiments on chemistry, because you might want things to happen fast. And having a lot of airflow is one way of making things happen fast. There's some other really important differences, and these are going to sound silly, but they actually are really, really important. Number one is, like, when we think about the typical residential HVAC system, and my house is included in this, like, it doesn't function very well. Sometimes it does, but a lot of the time, it's kind of built for bottom dollar. Compromises were made in its design for other things, aesthetics or space or other things. It wasn't really designed as much as, installed, usually by rules of thumb and that kind of thing. And so, there's also kind of a big difference in the amount of attention that's paid to the operation of that system. And I'm sure you've talked with Attila Novoselats before. And, Attila is a genius at all this stuff. And so, he makes really good decisions about the operation of that system to support the science. But that might be very different from in a real house.
And by the way, for those of you who are interested in hearing more from Attila, you can see him in several of the videos that I'm linking on screen right now. And that's for YouTube watchers. If you're listening to the podcast version of this, then go to the YouTube channel and search Attila on our channel. Okay, so, and then also there was a ventilation system, which a double wide trailer, I don't think there's a double wide trailer that I've ever heard of that has a supply only ventilation system that runs 24 hours a day.
Right. Yeah, absolutely. And again, that's to support the science. Remember, when you're, the way most of our systems operate, two really big operational differences is, number one, the vast majority of our systems in the US are recirculation systems, meaning that they don't even have fresh air coming in. The building gets its fresh air from leakage. right? Like there are gaps in the structure of the building that allow it to fresh air to come in. And then the other thing that's really different, and you alluded to this, is that our systems don't operate continuously. Your fan comes on with either air conditioning or heating when it needs to satisfy the thermostat, and then it goes off. And I've done a lot of measurements of runtime in thousands of homes, and typical runtimes averaged over the year are like a little less than 20% of the time, meaning 80% of the time the fan doesn't even run. So it doesn't matter what filter you have there. It doesn't matter all kinds of other stuff about the HVAC system. And so right away, the HomeChem, the fact that it has a ventilation system and that ventilation system operates continuously. And for the record, for a lot of the experiments, the recirculation system, that's doing the air conditioning in this house also operates continuously. So that operationally is kind of a whole different world.
Okay, so one of the things that they did during the HomeChem experiment was they actually tried to kind of like juice up the experiment a little bit by piping ozone into the ventilation system. And they were really surprised and also frustrated to find out that the ozone stuck to things on the way in and reacted with things. And by the time it actually got into the air in the house, there was hardly any of it left. And this is one of the things I'd like to just drill down on immediately, because it's a question I get a lot. UV lights or any other thing that's electronic. We kind of tell people on our channel that if it's not just a fan and a filter, it might influence the chemistry in your home. So can you talk about why, just because a company says that their product does not create ozone, that might not be the case?
Yeah. Okay. So first of all, let's be very specific here. UV light generates ozone when it goes below a certain wavelength. Okay. And there are other ways of generating ozone. The most common are a high voltage electrical current, either in a corona wire or in pins that can generate some ozone. And the way I always tell people, if you think about a photocopy room, maybe a small room with a couple of photocopies or even laser printers in them, you know what ozone smells like, right? It kind of makes your nose tingle. And that's because you think about a photocopier or a laser printer, there's a drum that's got a corona wire in it that charges the toner particle. The toner particles are charged and the drum gets charged by that corona wire. And that's what makes the image. And so it's the very same process in some things. So there is this really interesting issue that a lot of things do generate ozone. And then now we get into a question of, how much ozone is a problem. And you'll find some amount of debate on this, but there are a whole host of really important issues before we even get to that question. Number one is ozone is amazingly reactive, right? Like you can't, if I were to turn on a reasonable sized ozone generator in the office I'm in right now, the ozone would certainly go up, but it wouldn't go up nearly as much as you would expect because of all those reactions happening. And there's a lot of people like me describe it as surface area to volume ratio in an HVAC system. So there's a lot of surfaces and dirt and stuff for ozone to react with. So you can do a measurement and say, hey, look, I'm not elevating ozone at all. But that's just because you are elevating ozone and it's reacted away and formed potentially harmful things in that reaction. So that's issue one. Issue two is we tend to think about things as, oh, this must be a constant thing. So I turn on this electrical device, this air cleaner or whatever it is, and I get ozone. Actually, that can change over time. So for example, when the device is dirty, it might generate a lot more ozone than when it's clean. When that UV lamp gets ages and its output changes depending on the type of UV lamp that it is, it can emit more ozone because its wavelength is actually shifting. And so there's this, in addition to this problem of the ozone reacting away, there's this dynamics piece that's really important. And then the third thing that I should say is that, air cleaners, a lot of air cleaners are manufactured. They're not super high quality components. So there's a lot of times where we've tested two identical make and models of air cleaners. Let's say they've got a UV light in them. And we see a factor of 2 or 3 difference in ozone emission when they're brand new from the exact same device. And that's just, electrical component variation, maybe some other things going on with the electronics. And so, we're dealing with what's a pretty complex beast, even before we get to all the chemistry that I know you know a lot about, but that is also very complex in its own right.
And by the way, for our audience, I'm trying to get the most effective use of Dr. Siegel's time here. So we're not going to dive into stuff that we've already covered in other podcast episodes or other YouTube videos, because there's just so much to talk about. So we're going to have you back, and I'd like to hear things in your own words. But if we can, so to sum up, I have heard a few different things about UV lights. First of all, electronic air cleaners. Need them? Don't need them? If you got a good filter?
So I always say about any device, there are two questions. One is, does it work? Is it effective? And number two, is it potentially generating something harmful? And where I always come down personally on this question is, look, even if there's a potential for harm, why don't we use the filtration that we know works, or, there are some high quality UV systems, use those instead of going into stuff that we're unsure about. So that's where I come down on it. It's not so much that, I'm going to tell you, oh, that air cleaner is going to kill you, because that's not really what we're talking about here. What we're talking about here is there are better alternatives.
So do you mind telling us what your shopping list for things that are proven? Like, obviously we're all about filters. So anything that filters, MERV 11 to start with, 13, 16, charcoal, HEPA, those aside, what kind of UV approaches? I've heard that UVC is the safe way to go and expensive, but I don't know exactly what else to look for aside from those things.
Yeah. I want to say some things about filtration, but I'll answer your question about UV first. So the first thing I would say about UV is you really have to have a design professional involved, because there's not like an off-the-shelf solution here. And so the major...
I'm sorry. All the HVAC guys on this just went, wait, there's not an out-of-the-box. So, okay, please continue.
Yeah, no, absolutely. And so the major issue is, okay, if you want to use UV light, by the way, UV light only deals with microorganisms. So the major design factor is you have to make sure that the droplet containing the virus or the bacteria or whatever, as it passes by the UV light, gets enough of a dose to inactivate it. And so this is really a challenge. Like, if you go to a modern hospital, you'll see that they probably have UV lights in their HVAC systems, but those are just like so amazingly bright that they have all kinds of safety features. They immediately cut off if anyone opens up a door to access the HVAC system for maintenance, because think about the air, it's rushing by. It's got a split second to deliver its dose. So it's really got to be bright. And that's why a lot of the smaller systems are an issue. And then the second thing is, you got to make sure that your wavelength doesn't go below 238 nanometers, because that's where you start seeing ozone generation. And so that all sounds really simple, but actually gets really complicated really quickly. I've never looked at a UV system that has a really sharp cutoff in wavelength. So you're dealing with a distribution of wavelengths, how much below is okay. That gets where you want a design professional there. And, HVAC airflows are very complex in residential systems. And so, you have to really make sure that you're delivering enough of that dose. And then, like anything else with HVAC, and I know everyone hates to hear this, but there's a real maintenance issue here too. And so, you've got a bulb that you've got to change when the manufacturer says to change it. You've got to keep things clean to keep them effective. And, those of you who've looked in your HVAC system, it's not a particularly clean place. So if you do have bulbs, they can have stuff accumulate on them. You got to stay on top of those kinds of issues. And so it's not something like I'm going to say this and you'll get hate mail, but that's all right. I always kind of hesitate to recommend UV, because it's kind of like, yeah, you got to do it well. And if you're not going to invest the resources to do it well, then you're much better off doing something simpler that's tried and true.
Okay. So, in short, we have all these HVAC professionals in the United States going to their supply house and they're being sold UV lights. And anybody who's an HVAC professional could probably rattle off 3 or 4 brand names right now. Are you just saying, let's just stop using those right now?
Yeah, I mean,
And
I think
I will
that,
receive the hate mail, by the way. You guys, you're writing to me, not Jeff.
yeah. So I would say that, there's just so much caution involved, that remember that, I really do like HVAC professionals. I mean, I really do respect them as a profession. But I will say that, there are some messed up things in the distributor model. Like, they make money by selling an air cleaning product that may or may not be the most effective air cleaning product. They don't have necessarily the scientific expertise to evaluate some of the marketing claims that are being made by a lot of these air cleaning products. And so, I always say that, I'm sure there are great professionals out there selling really high quality UV lights, but I don't know a simple way to tell people how to say, oh, that's a good person to go with, and that's not. So, it's like everything else, do your homework. By the time you've done enough of your homework, you're enough of an expert, where I wouldn't say, no, don't use a UV. If you've done all your homework, you know exactly what you're going after. You're really sure on the ozone issue. You understand the costs and the maintenance and all those sorts of things. Then sure, it can be a great tool in the toolkit, but it's not something that I would jump into without that effort.
So, in closing up the chapter on our UV fire that we just set, I'm not a researcher or a scientist, so I like to just check. Is our approach that you can get the same goal of having no viruses and microorganisms flourishing in your house by just using reasonable approaches on air tightness, insulation, ventilation, and then designing and installing the HVAC system reasonably well with filtration? Is that you were going to say something about filtration, by the way, a minute ago?
Yeah. So, I could talk to you all day about filtration, and I know I talk too much, but let me just say something about filtration. Filtration has been used as long as we've had buildings, as long as we've had forced air systems. Filtration, its history is there. It's to protect the equipment, keep the fans and the surfaces clean inside. It has nothing to do with our health. And now we want to use filters for health. And that's a great thing to do. But where I often see the mistake being made is people focus on the technology, or the particular filter, a MERV 13, a MERV 15, or, this is a great filter that does this. And what we miss, and this is really the most important thing I'm probably going to say today, is like how that filter is used is actually, in many cases, much more important than that stuff. And so, for example, you go to any home and you look at the filter installation, you're probably going to see gaps around the filter. So you can put the best filter in the world there, and air, is going to preferentially take the easier path. It's going to go around the filter. And so the better your filter, and potentially the more pressure drop it has, the more air it's going to force through those gaps. And that's huge, right? And so something as simple as, making sure the filter is installed well. Where I am in Toronto, there's this very common thing called an open filter slot. So all of our furnaces are located in our basements. And, to make it easy to change the filter, there's just a slot at the side with no cover on it. And you slide the filter in. Well, that's like walk-in bypass, right? I mean, because, the air can go out before the filter, in after the filter. And again, the better your filter gets, the more that becomes. And then the other thing is, like, none of us change our filter as much as we should. And that's really a big issue, because for one thing, the same thing happens as your filter loads with stuff, you push stuff through the bypass gaps more. But then also, used filters are pretty nasty. As someone who studies them for a living, they've got a lot of microbiological growth, odorous stuff, other stuff on there that we don't want. So you've got to change that filter. And then, there's kind of layer upon layer here, but without going into too much detail, a lot of the high efficiency filters in the residential marketplace, in fact, almost all of them, are what are called electret or charge and media filters. And they have a really nice feature. They have a charge on them, put on them at the factory to help attract particles to them. So they actually get more removal with less pressure drop. Sounds fantastic, but like most things in life, it can be too good to be true, because what happens is that charge either gets masked or dissipates over time. And so, we have a big study we did of residential filters. We found MERV 14 filters not uncommonly behaving like kind of MERV 5 to 8 filters after not that much time. Some of that is the bypass issue, but a lot of that is this decline in performance as well. And so, again, like, I love filters. I could talk to you all day about filters, but, I really hope people don't stop at, I'm going to buy a good filter. And instead I'm going to use that filter well. That's if I can do nothing else in this world. Yeah.
Right. Okay. So, okay. I almost not like I feel lost in the labyrinth now. Okay. So so HEPA. Mm-hmm. Everybody makes what they call a HEPA. They're all different sizes. They're all made by different manufacturers. Like, is there someone like you, an independent person at a university somewhere, sitting down and actually saying, yes, this meets HEPA? Or do they just claim that it is, and then until somebody proves them wrong?
It's really complicated, but the short answer is there is a HEPA standard. And there are actually grades of HEPA filters under some HEPA standards. And I would hope that anyone making the claim that this is a HEPA filter is actually testing to a standard, a recognized standard for HEPA filters. Okay. But sometimes I think we make too much of the distinction. A HEPA filter, by definition, has got 99.97% removal for 0.3 micron particles. Those are a particle size that is very challenging to remove. It turns out smaller particles are actually easier to remove than that minimum, and bigger particles are easier to remove as well. So all filter efficiency curves are U-shaped. Okay. And
really, yeah. So yes. Can I just clarify? So you're saying that the 300 nanometers, which is 0.3 microns, is the hardest one. So if you've got it, that's the bottom of the U. Yep,
you got it.
Fascinating.
So sometimes it's a little smaller than that, like let's say 100 to 300 nanometers to be technically precise. But it's and so basically what happens is, remember that small particles are so small that they collide with all the oxygen and nitrogen molecules in air as they go through their travels in an HVAC system or anywhere. And that really knocks them around. We call that Brownian diffusion. And so that's why really small particles are easier to remove. And you'll notice that a lot of manufacturers are preying on this. They say, look, we're the only person who removes 0.007 nanometer particles or something like that. They're just preying on ignorance, which is perfectly reasonable. Who would think that smaller particles are easier to remove? But they're just doing that. Yeah. So
amazing. Okay. Because my next question was going to be, why did they stop measuring at 300? You're saying that if they kept going, then the number would get better. So we just stop at the 300.
Yes. Okay. And there's another nice practical reason too, for a lot of filtration testing, not necessarily for HEPA, but for a lot of filtration testing, that the equipment to measure particle size starts getting expensive and complicated if you want to look at smaller particles.
More expensive than it already is. I'm sure it's pretty freaking expensive already. Yeah. Okay. So let's, when you were talking about the MERV, which I just think is killing me, MERV 14 behaving like a MERV 5 to 8. So one of the big myths that's going around the social media is that if you let your filter get a little bit dirty, it actually becomes a better filter. Can you please, let's put this to rest?
That is flat out wrong. So there are filters out there that don't rely on charged media. They do get better as they age. In our study, our study was, we had 20 homes. We measured them for a year. So a nice long-term study. Each home had 4 levels of filtration over the course of the year, each for 3 months in a random order. We did a MERV 8 filter, a MERV 8 electret filter, one of these charged media filters, a MERV 11 charged media filter, and a MERV 14 charged media filter. And what we found is our MERV 8 filter, the uncharged one, the one uncharged one, first of all, it had the lowest performance, as you would expect, but also it didn't change over time. So I guess maybe it would have gotten better if we ran it for a really long time, but that's got a lot of issues with it because of odors and microorganisms and other things. You don't want to do that. All of our other filters, on average, declined in performance as they aged. And by the way, I know we're talking about residences here. That decline can be even much larger in commercial buildings. There are some amazing data out there in the literature that shows, a filter that performs at 70% at 0.3 microns when it's new, after a filter rated for a year, after 9 months, it's performing at like 15% at that same size.
Okay. Okay. So how would we know the difference between a not charged and a charged? It sounds like you're saying if I'm going out shopping for a filter today, I would be, based on what you're telling me, shopping specifically for a not charged filter.
No, I actually think charged media filters definitely have their place. And so it's kind of one of those things where it's a factor you have to be aware of. So many people might, for example, have a 1-inch filter slot. They can't.
Those people.
Yeah, I do. I have a 1-inch filter slot. I shouldn't, but I do. Okay. So if you have a 1-inch filter slot, that's kind of the standard, not that thick filter. You can't get an uncharged media filter of a high MERV. So you've got to make your decision. Do I get charged media filters and change them more frequently? Or do I get a uncharged media filter and get less performance? The right answer, by the way, is I should get a thicker filter slot. And then I can get a really good filter, a 2-inch or a 4-inch or a 5-inch filter. I tell people to do that because it's not that expensive in the grand scheme of HVAC stuff. But the real reason I tell people to do it is that the build quality of those thicker filters is better. And so you actually get like a better filter that's less likely to have bypass and everything. There's nothing magic about the thickness. It's just you get a better filter it costs money, but obviously you get, you're a little bit more guaranteed of the performance. The other comment I make about filters is, this gets into the weeds, but it's an important point because we might start seeing it in the residential market. So you obviously have heard of MERV. There's also MERV A. And so you might see a filter with a MERV 11A or a MERV 13A on it. What those filters mean is that they have been tested with kind of a discharge simulation procedure it's kind of an optional part of the standard in ASHRAE for testing filters. And so you can have a lot more confidence that if a filter's got an A designation, that it is going to perform over its lifetime at the MERV level. Right now, if you were to go to the home improvement store and say, hey, I want a MERV 13A filter, they're going to say, what now? Because it's not that common. But remember, to the big filter manufacturers, they don't much care about the residential market, right? It's a small market. It's kind of a messy market because everyone's got different filter sizes. And, you've got to convince each homeowner. You're not convincing, someone who manages, hundreds of buildings and buys, millions of filters. So it's a kind of a messier market, but this is where the demand would start, as consumers get much more savvy about their filter. Hopefully they'll do this type of thing and ask for it, and then we'll see it in the marketplace.
Amazing. Okay, so you're blowing my mind, and we're not even like that far into this. I will not take all day of your time, but can we talk about airflows? You talked about how complex airflows are. And I believe that I just heard from one of our other partners that there is really no such thing as truly like laminar airflow in a residential system, that is just turbulent, and it's different variations of turbulence.
Yeah, sure. I mean, airflow in buildings is fantastic, but it is a mess, right? Like it's in my own house, we have a house about 100 years old, a forced air system that was undoubtedly retrofitted some point later in the house's life. And, airflow is different, in the morning versus the afternoon, different on one day of the week than on the other day of the week. And there are all these factors. So obviously the HVAC system in the fan is a big factor. But even that has got, it's like peeling an onion. It's got layers of complexity. So again, we're going to nerd out a little bit here, but there are two types of fans that are commonly used in the residential marketplace. permanent split capacitor fans, and electrically commutated motor fans. I'm going to call those PSC and ECM fans. Okay, so PSC are the old standby. You always can recognize them. They got a big capacitor on the side. They'll run forever. So many times the fan will outlast the furnace or the air conditioner it's connected to. But they're really not that energy efficient at all. And also, they have this feature that as they see more pressure drop, they move less air, right? So as you have a filter with a bigger pressure drop there, or as your filter gets dirty, the fan flow actually gets less and less and less. And so you think about that. I mean, that does things to your air conditioning, it does things to your indoor air quality, but it also does things to your air movement in the space. And that's changing all the time. ECM fans generally, not always, but generally increase the fan speed to maintain the flow. And so they kind of compensate for that a little bit. But even so, you see all kinds of variations, electrical, other variations that cause variations in flow. And remember that, in the typical North American home, that fan is operating less than 20% of the time. So you've got 80% of the time where, other things are being really important to the flow. Natural convection from us, we're all little heat sources, and from our computers and all our electrical uses, you get buoyancy driven flows, you have leakage through the building shell coming in. Maybe you're one of the, I don't know what the number is, let's say 5% of American homes that has actually a ventilation system there. So that's going to influence your flows too. Maybe you've got bathroom exhaust fans. Hopefully you're using your kitchen range hood fan. That's all going to influence the flows. And so, the thing that I think is the kicker on all of this is that, I can count on my hand the number of times I've seen in the literature of someone actually characterizing those airflows on kind of a room by room basis for any amount of time in a residence. Right. So we don't even know what the number is other than it's really dynamic.
So first of all, I noticed that in the homechem house, which you helped to design, there are velocity sensors along the walls and the ceilings. And Attila had told me that based on just the temperature difference between the surface of the wall and the air right inside, that there was kind of convection that's always happening. Even if the HVAC system is not on and there's no ceiling fans on, the air in the room is constantly always kind of doing this. And it strikes me, or it has struck me before, that we used to have fires all the time. So the air was smoky, and people, I think, probably used to be very aware that we live in a fluid. But now it's so invisible. Do you think that there are kind of psychological side effects to the fact that we have totally forgotten that we live in a fluid most of the time?
Oh, absolutely. And I mean, I always say about indoor air, the hardest thing about what I do is that you can't see it. Dirty indoor air and clean indoor air functionally look very, very similar, if not identical to each other. Right. And so, there's airflows happening all the time, and, we don't see them. And I think we were talking about fire and smoke. I think that is true. And one of the ways we visualize smoke in a building is we create some artificial smoke and watch what it does. And it's always really instructive, and it's always really different when we see that. But I think that that's kind of the whole problem with indoor air quality, is that, it's kind of out of sight, out of mind. And frankly, until we had COVID, unless you're one of the people who suffer from allergies or asthma, we didn't think about indoor air too. All the health effects we were talking about were chronic health effects that took effect, decades down the road. So we're not very good at even caring about stuff that happened so far in the future. That's just kind of not how we're wired, or not how we're built. And then you add to it that, we can't even see it. And then you add to it that there's all these kind of snake oil and kind of bogus stuff going on in indoor air. And it kind of makes for a, kind of a perfect storm in a lot of ways. But I'm always surprised at the number of times, I've been on a little kick lately about humidifiers and about how much stuff is generated when people use humidifiers. And the number of times I've been talking about this with someone, even someone in the business, but even, more generally someone. And they're like, oh yeah, I always see that line of white mineral deposits, around my humidifier whenever I use it. It's like, yeah, that's stuff that, you're not seeing most of it. It's going into the air and you're breathing it, and so there's all this times where even when indoor air does become visible, we don't make the connection that it's indoor air.
Really? Yeah, absolutely. Okay. So as far as ventilation goes, you said something like 5%. It is, I think that a lot of, it's like, I don't know what it is, whether we're humble. I don't think it's that. Americans are not known for that, but we tend to think that it's better. The building industry is better in Canada or in Europe. And I believe that that's probably not technically the case based on actual numbers. Can you kind of clear up? Because I tend to have clients who are from Canada sometimes who are like, oh no, we don't have blower door tests here, or we don't have ventilation systems that are required by code. How is the situation in Canada as far as the things that you research?
Yeah, so Canada is functionally very similar to the US. I've lived in cold climates in the US, cold climates in Canada, marine climates in both the US and Canada, California, Texas. There's always regional differences, frankly, which are much bigger than anything else. But by and large, the building industry, especially the residential building industry, there are great people working in it. There are people who are just there to make money and do stuff cheap and don't care about any of this stuff. But by and large, Canada and the US, I would say, are pretty similar to each other. There's probably some people who get mad at me for that, but that's probably more or less. Europe is completely different. So you think about 80% or so of American homes have central forced air systems, either for heating, for cooling, or for both. The number is lower in Canada. It's just over 60% or so. But you go to Europe and the number is, functionally zero for forced air systems. It's all, hot water systems. In some cases, we're seeing more of mini splits or, distributed heat pump type systems. And then they have ventilation systems, but they're really ventilation systems. It's fresh air coming in from outside, sometimes through a heat recovery ventilator or something like that. And the idea is to provide ventilation. So I think it's really interesting that until, relatively recently in North America, we've gotten away in our residents from even the idea of ventilation systems. You think about, first of all, most homes until recently and only in specific parts of the country it's just a recirculation system just for heating and cooling. So don't have ventilation at all. And to the extent they do have ventilation, it's things like kitchen fans, bath fans, which probably don't work and are really noisy anyway. And so it's not even part of how we think about things. And yet we still call them ventilation systems, or we still call them HVAC. It's like, yeah, but there shouldn't really be a V there. They're heating and cooling systems. Whereas in Europe, they say air system or ventilation system, they mean fresh air coming from outside.
So in a home, we just built a high performance home, me and my parents, and I am using the central air, the duct system, which, some people, when they find out about ductless, they're like, oh, let's just do all that all the time. And I have a ductless right there, and I know what it takes to actually clean and maintain that, which I think is something probably you know a lot about. But I think that if you don't have a duct system, then how are you circulating and filtering the air? Can you talk about how they do? Is it like they have like a room HEPA unit in every single room of a house in Europe? How does that work?
Yes, that's right. They're doing some other solution for air cleaning, usually portable room air cleaners. And by the way, that's first of all, remember our central systems, most of them have filters in them that are to keep big chunks of stuff out of the system. It does nothing for our health. So this idea, even though we have a central system, we're not using it for indoor air quality. But to the extent we're starting to use things like mini splits and so on, which I love, for the record. Let's be very, very clear. They do not do air cleaning. Mini splits are highly
the opposite sometimes.
Yeah. They're very efficient, but you can't put a filter with any amount of pressure drop because you'll really kill the performance of the unit. And so, I think that if you do use ductless or even for those of us with central systems, because our systems don't run that much of the time, then you really have to think about some other air cleaning solution.
Interesting. Okay. So can we talk a little more about the difference between, we like to think that the way that we do it here is probably the best way. Are there better ways according to the results that you're actually seeing from the health of the indoor air?
Oh, absolutely. I mean, you can't assume ventilation is going to happen. The best building is an airtight shell with dedicated provided ventilation. And, I like windows and open windows, but, not always we can use open windows. And talk to anyone who's been impacted by wildfires, and they'll tell you just why they can't open windows all the time, not to mention heat and cold weather and outdoor air pollution and other things too. So, you build that airtight box, you supply ventilation that you can treat if you need to with filters or otherwise. And, that is the healthiest indoor environment. The closer you get to that standard, and let's be fair, some places in the US, some builders in the US and Canada are doing that. But, right now, I think the problem is, if you say to someone, do you want a healthy house? Of course, we'll all say yes. And then you say to someone, okay, so here's what it's going to take. I'm going to have to spend all this money on, the enclosure that you won't see. I'm going to put in this, heat recovery ventilator and distribution system for the ventilation air that's got filters you're going to have to change. And, it costs, a lot of money in the cost of a high performance house. And we just don't value it. Like the example I always give is the kitchen example. Like when you're doing a kitchen renovation, you think about the countertops and the appliances and the fixtures and all that stuff, but you never think about the range hood fan. But that's the thing for most of us, assuming we're not smoking and so on. That's the thing that number one is going to determine whether we have a healthy house or not, is, a good kitchen range hood fan that we use. And, I know you've probably dealt with that other places, but, it's just kind of funny that we don't have that wired into the way we think about residential construction. I collaborate with someone named Mike Mack in psychology, and we've been doing a bunch of experiments around cognitive function where we expose people and then they do a standardized cognitive battery and we look what's going on. And where we were right before COVID is we were all set to go into an MRI and image people's brains as we expose them to things. And then see if we can, his belief is that we'll come up with a neurocognitive model of exposure. So not only can we say, hey, there are these cognitive effects and we should be thinking about that, but that, we can build a model of this and can actually, not to be too crass about it, but kind of come up with an explicit value proposition for cleaning the air because you see it right away. And my goal in this is not to talk about the health impacts. They're real, they're huge, they're big dollars, but they're not motivating. Instead, let's just do it all with these cognitive impacts and then have the health benefits just kind of accrue in the background, kind of the positive externality of indoor air. So that's where I think, we're years away from the reality of that, but already this is being used. So how many times have you gone into a store and noticed a scent in the store? If you look in the retail literature, that's done for a reason. And one of the big things that we found in our own research, and I assume is well known, is that people are more likely to make impulsive decisions when they're exposed to some scents. And so what's happening I don't know how deliberately this is being done. I'll make some assumptions on my own, but that, this is being done. Scents are being added to make people spend more money in retail environments. And so, already this is happening. And I'm just saying, let's kind of turn this into something that's maybe a little bit more positive. Let's improve indoor air by paying attention to this rather than, trying to improve profitability or something like that. So, and one of the sources we've been exposing people to, you mentioned VOC, so I'll say this, is essential oil diffusers. You know what an essential oil diffuser is? It's a little ultrasonic humidifier. You put water in, a few drops.
That's how you transcend your reality and become cognitively perfect, right?
Yeah. So essential oil diffusers are crazy in how much air pollution they put into a space. Like there's a ton of particles from the oil, and those oil particles are really reactive. And so there's kind of a whole second layer that we haven't even explored of, what kind of chemistry is going on. But then the water, like tap water, is full of minerals. Lots and lots of people have done research on this over the past few decades. It's this huge particle generator. I mentioned that before. So I think there's something really interesting. You're taking this device that we think, because it smells good, is having a positive impact. And not only is it got some pretty serious things of concern coming out of it, but it's also, manipulating your cognitive function.
So would you say that treating water, that purifying water becomes at least an ingredient, if not a central ingredient in air quality?
If you are using an ultrasonic or a cool mist humidifier, and you are using anything other than the purest distilled water you can get, you are asking for an air pollution issue.
Right. Well, we'll keep on trying to preach on that along with you. This has been so fascinating, and I've got other questions that are going to pop up. And if you are watching this on YouTube, comment below if you have other things that we want to come back to Jeff with, because you're a badass. And also, if you ever come to Atlanta, please give me a call and we'll take you to dinner. And then I would just love to walk you through our house and just have you talk about things as they occur to you, because I'm sure your mind is a pretty fascinating place to just wander around in.
Yeah, people don't always say fascinating, but yes.
Well, thank you so much for your time today. And again, I hope that you will join us again in the future. Dr. Jeffrey Siegel is a researcher on indoor air quality and HVAC systems, and is a professor of civil engineering at University of Toronto. Thank you very much for listening. As always, if you'd like to be more involved in this process, number one, we have a Patreon membership that you could give as little as $5 a month, and it helps us to justify making these free resources and spending time making them nice and editing them and all that stuff, which I do here in the Tiny Lab. You could also come and train with me in Atlanta. We have 4-day trainings going on every 3 months. That's March, June, September is the next one coming up, and December. They are 1 day at a time, but you can come and spend all 4 days with me if you'd like. We get hands-on with testing and all kinds of principles of ventilation and HVAC and enclosure diagnostics. Also, you can stay now in this tiny lab that I'm talking to you from. We are hosting overnight guests who want to learn more about performance and feel what a high-performance home really is like. Listen to it, smell it. All of that stuff is very useful when you're trying to get better at this niche that we all find ourselves in. Thank you again for super nerding it out with me on this episode. I hope that you'll tune in again.